Oh, sorry for being a bit late. Hi, Ben. Good to see you.
Hi. I'm gonna be
I'm
doing.
yeah, making you the co-host. So,
Yeah. Oh shoot. Sorry. Just a second. Um,
looks good to me.
I'm gonna be also joining from my other computer so that I can see people.
Okay.
What the? It's asking me to update, and I've already updated. It's fine. I can just join later.
Good morning.
Morning.
Yeah, good. Ah, cool. Yeah, let's wait a minute or two for people to wake up. At least for me,
Yeah.
this is early.
Yeah. That's fair. Can you see that I'm writing something? I've been having trouble with that lately.
I don't see any writing except, co-spectral radius for inclusions. Oh, I see it now.
Okay. Yeah. It's for whatever reason, like when I leave and then unleave, it like makes it so that you can see it.
Okay.
I see the pen and eraser cursor, but no writing still.
Well, that's because
It's
I
not moving. Oh. Yeah, there we go.
Hmm. So are you in Virginia, Ben?
Yes, this is my apartment. I'm in Virginia. Uh, I don't have to teach today, so today is my research day slash not going to the office day. Also, I had a meeting just before this one, so I wasn't going to get into the office that early. But yeah, I've tried to block off Fridays to just do math. Uh,
Nice.
yeah.
Well, I'm excited to hear your talk. I guess it's a good time to start. Are you ready?
Yeah, I can start now.
Okay, we're happy to have Ben Hayes from University of Virginia talk about co-spectral radius for inclusions of equivalence relations.
Great. Thanks. Thanks, Louis, for the introduction, and thanks for inviting me to give a talk. So I'm going to start with a definition. I think maybe given the name of this seminar or the series of talks, this might be familiar to everybody, but just to make sure we're all on the same page here. So X mu will be some standard probability space. So we'll say that R is a discrete ENP equivalence relation over X mu. If R is a subset of X times X, which is Borel, I want that the relation Y equivalent to X if and only if X, Y is an R is an equivalence relation. So I'm just thinking of relations like logician. They're subsets of x times x. And I want that for almost every x, the R class of x, which is the set of y's, so x, y, and R, is countable. And lastly, I want that the mass transport principle holds. So what does mass transport say? It says that for every Borel function non-negative, the integral over x of the sum over y and x, f of x, y, d mu of x, is the integral over x, the sum over y equivalent to x, f of yx, d mu of x. Right, so like on a graph, you'd see, you sort of think of f of x, y as like a mass from x to y. And instead of saying that the total mass coming out from x is equal to the total mass coming into x, I'm saying that that's true on average. So the example you should be thinking of is I take some PMP action of a group, which is countable group, and I just look at the orbit equivalence relation. And it's an exercise to prove that saying that the mass transport principle holds is equivalent to saying that this action really is PMP. Okay. And it's a theorem by Feldman and Moore that all such all are of this form. You can't force the action. You cannot force the action to be free. But if you just ignore that, all equivalence relations arise like this. Okay. So what so the point of this is that somehow we've abstracted away the group action and we've turned it into a relation. But that actually buys us some interesting things. So free actions remember much of the group. So for instance, I can define amenability, property T, lots of other things, anything sort of defined in terms of representation, unitary representation theory of the group, for relations, and then they're equivalent to the same property for G if R is RGX, and this action is essentially free. So for every non-identity group element, the measure of the set of fixed points is 0. Great. And so in our case, what we're interested in is inclusions of equivalence relations, using this notation to mean that S is a sub-equivalence relation. So just a subset, which is also an equivalence relation. Okay. And in particular, we're going to be interested in the co-spectral radius. Now, all of the situation is meant to be analogous to the inclusion of groups. Maybe let me give you one non-group example, or not obviously group example. I think it's genuinely not a group to motivate this. So I could take G, a finitely generated group. S is a bad choice. We call it T. If I can write. So G, a finitely generated group with finite symmetric generating set. And I look at the Cayley graph. And I do edge percolation on the Cayley graph. So I fix P between 0 and 1. And I look at the Bernoulli measure. So I want to make sure I do this correct. There's all these conventions about percolation. And I want to make sure, right, so I'll put 1 minus P delta 0 plus P delta 1 to the edges of the Cayley graph. So this E of Cayley GT is the edges, set of edges. Okay. Now, if I have a point in 0, 1 to the edges, I think of this as giving me a subgraph. So call it gamma sub x, subgraph. Where the edges here are just the set of edges that I had before. Where the value of this function is 1. Okay, so if I put a 1 on this edge, it's kept. If I put a 0, it is gone. Right? So I sort of keep each edge with probability P, and I do this independently. And I get this subrelation, which is the set of all GXX, so that G inverse and H inverse are connected in this graph. And this is a subrelation of the Bernoulli relation, the Bernoulli action. And saying interesting things about this subrelation is telling you things about this percolation. Okay. So that's a good example to keep in mind. So you can turn percolations into subrelations and annoy all the percolation people. Okay. Let me throw another definition at you. So I'm going to start with the group case and then explain the difficulties that arise when we try to generalize this to the relation case. So let's say I have a measure nu, so probability measure on G, which is symmetric. So the value of any, the probability of any group element should be the probability of its inverse. Remember, my group is countable, so all these measures are atomic. Then I get a random walk on G, starting at the identity with transition probabilities. Nu of Y inverse X. And the nice thing about it being symmetric is I don't have to worry about if I'm multiplying on the left or the right because it doesn't matter. So, okay, that's convenient for people like me who are bad at keeping track of these things. And so I can look at P2KH. So H here is a subgroup of G. And this is the probability that the random walk is in H. Let me say K, after K steps. Okay. And then what is sort of the co-spectral radius? So in this case, it's literally just a spectral radius, is the limit as K goes to infinity of P2KH to the 1 over 2K. And we know that this limit exists because this P2K thing is super multiplicative. And you know that's a real analysis exercise that the limit exists from super multiplicativity. That has already been in my students' homework. So, okay, great. And the other nice thing here is that I can realize this as the norm of a certain operator. So that's not as much a real analysis exercise, although there's some, it's not a triviality. but there are some short proofs. So here lambda G mod H is the sort of quasi-regular representation on L2 G mod H. Implemented by the action of G on G mod H. Great. And everything I've said so far is I don't even really know who to attribute this to because it's all relatively classical. And I mean, this part is probably the hardest, but you know, this is all stuff that's like pretty well established for beyond even groups, just even for graphs. You know, I can use adjacency operators and things like that. Great. So what about the relation case? Okay, so the relation case is meant to be analogous to the group case, right? I sort of said you can think of relations as sort of like generalizations of groups. In a sense, you know, if I have a free action, the group is kind of like a lattice in the relation. So, you know, sub-relations should sort of relate to subgroups or something. So, all right, well, let's first just start by copying the setup. By the way, feel free to hop in at questions anytime. Like I said, I had a meeting just before this, and so I had to wake up a little bit earlier than expected, and so I'm a little too caffeinated. So apologies if I'm going too fast, but feel free to hop in anytime. Oh, I forgot to mention. So to copy the group relation, I'm going to need to first talk about the full group. So these are the elements from X to X, which are bi-measurable bijections. That just means that they're bijections and it and the inverse are measurable. So that phi of X is in the R class of X for almost every X.
Yeah, maybe it would be good to say something about the intuition of spectral radius. Like,
yeah,
you know, just to say like, okay, if G mod H is amenable, then the spectral radius is 1.
Yes. So if H is normal, come on. Oh, joy. It doesn't want to play today. There we go. So if H is normal and G mod H is amenable, then the co-spectral radius is 1.
And that kind of means that the rate of return of random walk is sub-exponential.
Yes, yes. So the rate of return of random walk is sub-exponential. So for H being trivial, this is an if and only if. I guess, you know, when H is normal, this is an if and only if. When H is not, I guess there's some issue with what you mean by co-amenability and things. Well, no, wait, no, that's still, I believe, true. Anyway, yeah, right. So this is saying that the rate of return of random walk is sub-exponential. There's this interesting thing that like polynomial decay of the rate of return is equivalent to polynomial growth of the group, but exponential decay of the rate of return is not equivalent to exponential growth because it's equivalent to non-amenability.
Yeah. Right.
That's a bizarre thing. Great. And yeah, this is a well-studied object with lots of applications. Already this connection to operator theory is useful. Yeah. Okay.
And like the spectral radius of G when G is a free group of rank R, I guess is like 1 over square root of R times a constant.
Yeah, I think the spectral radius of FR with respect to the uniform measure on the standard generating set is it's like twice square root 2R minus 1 over 2R, so square root 2 minus, it's this. And that's actually something you compute, and this is, you know, you can now give a probabilistic proof. You can compute this using like generating functions. This is in Wils's book. Just Google search that. And this is something you can compute to give like a probabilistic proof of non-embeddability free groups, if you like that. Okay. Great. Other questions?
You call it spectral radius or a radius. Is there an operator involved in all of this that is you're taking a radius of?
Yeah, so that's a self-adjoint operator because the measure is symmetric. And so its norm is its spectral radius.
I see. So it's just the norm of this. Okay. Okay.
Norm of this operator. Yeah. In general, if the measure is not symmetric, I will need some reversibility. It's still the norm of a self-adjoint operator on a different Hilbert space that I sort of weight by the thing that does the reversing. And I guess that's conjugate to the original operator, so it has the same spectral radius but different norms. But I'm going to talk about symmetric measures. Everything's a norm.
Okay.
Other questions? All right, so let's return to the inclusion of subrelations thing. I need to look at this full group because that is the way that I sort of abstractly get at the group. This is the way that I tell you the group without telling you the group, right? As I tell you the full group. And so I could just take a probability measure on the full group. Let's say that it's countably supported. I don't have to take a countably supported measure, but this is a talk. We're not going to get into the technicalities. And symmetric. So the measure of a full group element should be the measure of its inverse. So this operator I write down as self-adjoint. Okay, and so I can just do the naive thing. I can take a random walk on the R equivalence class of X, starting at X, right? I think of my X as sort of being like the group element, identity element in this R equivalence class with these transition probabilities. So this would be nu of the set of phi, so that phi of y is z. Again, because this is symmetric, this is also the set of the nu of the set of phi, so that phi of z is y. So don't worry about this so much. And now I can look at this, which is the probability that the random walk is in the S class of X after 2k steps. Or k, which is 2k. And now the question is, does this limit exist? Almost surely. Is it a spectral radius? Does it have anything to do with amenability? Does it have anything to do with other things, etc.? Let me convince you that it's not obvious that this thing exists. But first of all, I don't have this homogeneity in general. So if I start at two different equivalent points, returning to a subrelation, unlike the group case, is not it's not the same thing. There's no obvious supermultiplicativity. I don't have anything like this. So just to be clear, I'm saying this is bad. If you write this down, this is because if you return to, it just basically boils down to the previous point. If you return to the subrelation, you're not back at X, and what's really happening here is that I can take the R class of X and divide it into S equivalence classes. That's fine. It's a subrelation. I can restrict the subrelation to the R equivalence classes, and that gives me an equivalence relation on the R equivalence classes. This is a thing that I can think about. But I mean, this thing absolutely the hell does not act on this. That's not a well-defined action at all. The only thing that acts on this is like the automorphism group of S, and that's like way smaller. So there is a quotient object, but it doesn't come with a nice group action. And so I can't just, I can't just copy word for word the group case. And so it's very not obvious. Okay. Let me first start by addressing norm, and then stating the theorem on existence. So because I'm in the 3-person group here, because I'm the operator person, I will start by telling you about Hilbert spaces. I will inflict this on you. So here's how we're going to fix at least the norm part, and then I'll address the almost everywhere existence part, which is the harder part and the more interesting part. So I'm going to find this new space Y, which is given by pairs XC, where X is an X, and C is the S equivalence class of something which is R equivalent to X. Okay. So this is like taking your L2 of G mod H before, except right now I have an L2 of G mod H over every point. So I have kind of like this like vector bundle, this like Hilbert bundle over points, and I sort of look at a total space. I just put them all together. So the action here is not well defined, but on the different fibers of this bundle. But if I take the bundle sort of together, I can act on that. I can act on the total space. Okay. So I need to define the total space. I need to make this into a measure space. By the way, I should mention this has a standard Borel structure. That's not so obvious, but I can declare a subset to be Borel if and only if for every phi in the full group, E phi, which is the set of X and X, so that X S equivalence class of phi X is an E, is Borel. And you can check that that's a standard Borel structure. Okay, so that's fine. And now I'm going to define this measure mu tilde on Y, on the Borel subsets of Y, by mu tilde of a Borel set is the integral over X of the cardinality of the set of C, so that XC is an E, d mu of X. So now I have an L2 space, and I can define a unitary representation of the full group on this L2 space. And the way that I'm going to do this is, well, acting on the equivalence classes is a no-no. That's what I said before. So I just shift the base points. So instead of acting on the fibers, I shift the base. Okay. And you can check that that's a unitary representation. Questions? Okay. So our theorem is the following, in the above setup, for almost every X and X, this pointwise defined co-spectral radius exists. Okay, that's already not obvious. Secondly, I can recover the L infinity norm of this function as the limit of these averages, well, these sort of exponentially weighted averages, exponential growth rate of these integrals. And that is the operator norm of this self-adjoint operator. So this is my notation for nu of phi, lambda s of phi. Okay. Great. And then lastly, if R is ergodic, standard assumption, You can always reduce to that by the ergodic decomposition. And if either S is normal, which don't worry about what that means if you don't know what it means. If you know what it means, then you know what it means. If you don't worry about it. Or S is ergodic, then rho sub S is almost surely constant. Okay. So in general, what you can prove is that this rho sub S is invariant under the full group of S. That's not so bad. You can also prove that it's in some sense invariant under what I would call sort of the partial normalizers of S, which is a little bit harder to define, but gets you the corresponding result when S is normal.
So you gave as an example of a non-group situation, percolation.
Yeah.
What does that say? What does this theorem say in that case? Or maybe you're going to get to that.
I was going to get to that later, but I can do it now.
Either way.
So if G sub P is this Bernoulli P percolation, okay, I could take a measure on my group, gamma sub P. Gamma sub P is what okay. Let me just call Bern P. I could take a probability measure on my ambient group. Remember, my group was finally generated, etc. I could take the uniform measure on a symmetric generating set. That's fine. And I could run the usual random walk. On the Cayley graph, or on G, really, the vertices of the Cayley graph. And then I could look at the probability. I don't know what to call this. Let's say Q2K. This is the probability, the random walk. So this is the usual random walk on G, not on the percolated graph. That after 2K steps, 1 and, or E rather, and well, after 2K steps, you're in the, the percolated graph connected component of the identity. So you're doing a random walk on the unpercolated graph, and you're asking, when do I land back in a connected component in the percolated graph? And this is saying that this limit exists. Almost surely, right? It's a random thing. Okay. And I might get to this later in the talk, or maybe I can get to it now. But percolation theory, people care a lot about with critical exponents. Yeah, maybe let me just mention it now. Do I want to mention all of them? There's a lot of them. All right, let's just do this now. So in percolation theory, people care about these critical exponents. I could look at the infimum P, so that G sub P, or burn of P, I needed better notation, has unique infinite component almost surely. That's the uniqueness phase. There's the existence phase, which is when burn sub P has one infinite component. And the big question here is, if G is non-amenable, does this imply that PC is less than PU? Okay. So one must mention the nice results of Igor Pak, and Smirnova Nagnabida, probably said that wrong, sorry. Which is that, there exists a generating set, for a given non-immutable group, there exists a generating set so that yes, okay. But the question is still true for all generated sets. And this is related to a bunch of other critical exponents. So I could look at this thing that the probability at this Bernoulli percolation parameter P, that X and Y are connected in the percolated graph, being less than or equal to some constant exponential minus some other constant of the distance between X and Y squared. And I can look at another thing I can look at is this operator on finitely supported functions on the group. Sort of similar to the above, probability that X and Y are connected. And so then there's this other parameter. Okay, and we now have 4 critical exponents. So I'm going to give you now 2 more. So this is this subrelation, this connectivity subrelation. So what is the largest P so that the spectral radius is the spectral radius of the whole thing. So the spectral radius of a relation is just when I take the trivial subrelation, and that exists by sort of standard methods. And then there's sort of the poorly named, but we couldn't find a better one, sort of co-amenability subrelation. What is this one? So I don't know if I mentioned this, but in the theorem above, this quantity, not this one, sorry, the quantity in 2. This quantity is called the sort of big co-spectral radius as opposed to the pointwise defined things. Okay. Great. And you can see various nice things like, well, it's what's known in general is that for the ones before us, PC is at most P22, is at most PXP, is at most PU. And what we prove is that we can sort of compare these. So the sort of Ramanujan spectral radius is at most the co-amenability one. The co-amenability one is at most PU. The PXP is at most P co-amenability. And the P22 is at most the sort of Ramanujan one. Okay. Does that answer your question? Probably too much. That probably was too detailed of an answer. I probably tortured people. Okay. Other questions?
So this is, I guess this is in the paper. I don't know. Is it?
Yeah, this is in the paper. This is like the last section of the paper.
Oh, okay.
Yeah, this is in the paper.
So it looks like it should be possible to get concrete answers to these questions when the group or when the equivalence relation is hyperbolic, like it has a hyperbolic graphing or something that's compatible with the measure.
So we started trying to think about this a lot in the hyperbolic case. The main thing we could get is this application to unimodular random trees.
Oh, okay.
Maybe I don't know what people would prefer me to talk about. Maybe nothing. I don't know. But I can either give you this application to unimodular random trees, or I can say a bit about the guts of how you actually prove this existence. I won't get too technical, but I can mention the main thing, which is this: how do you get almost sort of supermultiplicativity? I don't know. What do people think is better?
Kind of interested in both.
All right, let's start with applications. And maybe I will just be a little light on the details of those main application. We talk about a lot of things, how this is related to, there's other interesting questions on percolation that we give a nice answer to in the case of property T using this co-spectral radius. I'll just focus on one application. Okay. So here's a definition. So a unimodular random graph is a probability measure new on isomorphism classes of rooted countable graphs, GO, which satisfies a similar mass transportation principle. So for every sort of measurable or L, whatever that means, non-negative function, if I expect against this measure, right, if I integrate the vertices, you know, and I look at the weight coming out of the root, I'm going to compare that to the average of the weight coming into the root. Those should be the same. So this just means that nu is invariant under this relation of forgetting the root. This is what's called the rerouting relation. Right, so they're isomorphic as unrooted graphs. Fine. Now you can get this by sort of just taking full, just taking elements in the full pseudo group and using that to construct a graphing as you know, as you do. Those of you who've done this before know what that means. So there's this question of Kajmanovich, which is that if TO is ergodic, unimodular random tree. So it's ergodic under the relation of this rerouting equivalence relation. That's what I mean by ergodic. Does the growth, which is, you know, I look at the n balls and I take their exponential growth, does this growth exist? And the answer is no. This is by Timar. But the result is a one-ended tree. Okay, so it's just a line with some fuzz. A line with a bunch of finite fuzz. Okay. And the main one of the sort of coolest applications we have, which sounds like a joke at first. So if I have a one-ended unimodular random tree and its degree is at most d, then first of all, well, this is probably folklore. This is not, yeah. So that's not maybe originally due to us, probably not. But what is due to us? So the bar here means I take a lim sup instead of a limit, right? So the joke is as soon as the upper limit exceeds this threshold for the one-ended case, then the growth exists. So it's like, you know, it's saying that if the lim sup is sufficiently large, then the lim sup is the lim imp. And it's not saying it for sort of silly reasons that like the lim sup is as large as it could be or something. You know, just as soon as it crosses sort of this threshold that is a sort of easier bound in the one-ended case, as soon as it crosses that threshold, this works. And what goes on here is there's this. Okay, I don't want to get too much into this, but this uses an analog of the Cohen-Grigorchuk co-growth formula. So what that does is it relates sort of the co-growth of some normal subgroups to the co-spectral radius. And it sort of also uses that I can turn this unimodular random tree and I can turn it into an inclusion of S into some subrelation, actually the same sort of subrelation, this connectivity subrelation that I talked about before inside, and I will slightly lie here, but you know, action of a free group.
So here, you don't have any obvious measure for generating the random walk, unless it's, I guess, just like a simple random walk.
Oh yeah, sorry, this is for simple random walk.
Okay, that's what you're.
Yeah, the above statements don't mention any random walk.
Yeah, yeah, that's why I was trying to, you know, connect it with what you were saying previously with co-spectral radius and so on.
So, but it uses that we can turn this one-ended unimodular. So we can turn this unimodular random tree, not necessarily one-ended, this unimodular random tree. We can turn it into a subrelation of a, you know, treeable relation. Right. We can turn it into a relation inclusion.
Right.
I guess I have what, 5
Oh,
minutes?
that's, yeah. Well, yeah, depending on how much time, it's probably best to end in 5 minutes if you want to have questions, because people will start, you know, some people will start leaving.
I don't want to waste people's time. Sorry, I think you're in the middle of saying something.
No, go ahead. I'm not.
All right. I'll do one thing about the guts of the proof. So we don't have this super multiplicativity, but we have some sort of restricted version. So if I take the square of this P2K thing, so I would expect this typically to be, if I had super multiplicativity, I would expect this to be at most P4K, right? I don't have this. But what I can do is I can do some Cauchy-Schwarz in a clever way. Maybe let me skip some of the brutal details, but this is, you stare at it long enough and realize it's Cauchy-Schwarz. That's my life. Okay. So that's true. This is P2KXY, P2KYZ, P2KXY, and then times the inverse of the sum of basically what I'm inserting in here. And that's Cauchy-Schwarz. So we'll call this phi k. And the important thing is that the mass transport principle tells me, so this is phi k of x, tells me that the integral of this function is 1. You can just use the mass transport principle to directly see that. When you swap the x's and y's, you get the sum of you get the sum over the same sum, which is 1. Okay, and this thing here is sort of, if you think about it pretty clearly, at most P4K XS. So I don't get the super multiplicativity, but I get it off by some factor which integrates to 1. So I get it sort of on average. And I can do a similar thing. This is actually harder, so this is me cheating. I'm saying similarly for the harder part of the inequality. It still admits a short proof, but it's like one you have to stare at for longer. Where this factor also integrates to 1. Now, what do we use? We don't know anything about these sequences, how they're related at all, right? All we know is that they integrate to 1. But if you have a bunch of things with integrate to 1, then they can't grow too fast as k goes to infinity, even if they have no relation to each other because of, well, swapping sums. So for all sufficiently large k, psi k of x, all large k depending upon x, is at most k squared. Phi k of x is also at most k squared. For almost every x, this can grow at most like a polynomial. whatever it is, just from the fact that it integrates to 1. And then, you know, you can sort of work hard from here. Now I really will want to avoid this. This is at most some product of some sort of sub-exponential terms because it's a bunch of polynomials. And now I'm actually lying to you, but it's true up to epsilon. Okay, and now if you stare at this for a bit, you know, this is true for all sufficiently large L. I can let R plus Q go to infinity, and then L go to infinity. And I can get, after some work, that the upper co-spectral radius is at most the lower co-spectral radius. And sneakily, what I'm using here is that, and Doug will like this because he made me do this once. The limit as x goes to infinity, you know, over the real numbers of the inf over Q and R of x minus 2 log, Q log 2 minus R log 3 is 0. Okay, so it uses that log 2 and log 3 are rationally independent. So I snuck in some actual dynamics in there. Well, this is all actual dynamics, but I stuck in some more classical dynamics in there. And that's the main thing I want to say about it. There are other things I could have mentioned about connections to property T and other interesting questions we asked more directly about this co-spectral radius itself. But I've probably you know, got too much into the technical guts at the end there, so I probably have taken up enough of your time, so I'll stop here.
Let's thank Karen then. So, you know, if you have questions, just unmute your mic and ask.
So Ben, if you have time, what's the collection to property T of the group?
Yeah, just a second. So we were asked this interesting question. So if this Bernoulli percolation has infinite components, almost surely, does this imply that this co-spectral radius is less than 1? And the theorem that we prove is basically that this is true if the group has property T. So if I look at kappa, which is the Kasdan constant of GS, so G is the property T group, finally GT, say, oh, GT is also bad, GF. So G is finally generated by F. Metric. So by this Kasdan constant, I mean that this averaging operator that everyone likes is less than or equal to kappa if pi has no invariant vectors. So if the co-spectral radius is larger than kappa, then this Bernoulli percolation has infinitely many components, almost surely. Has finitely many, sorry, finitely many. And basically what this goes through is that, you know, once this happens, this action of R on L2 of R mod S, or L2 of Y, we were calling that R mod S in the paper. Once this constant is, you know, once you get bigger than the constant, you have to have a fixed vector, and you can just flat out characterize what it means to have a fixed vector in here. It basically means that S is finite index in R after restricting to an S invariant subset. So, okay. And then that gets it to you if we unravel what it means to be, you know, to have finite index. If you unravel what it means for this connectivity subrelation to have finite index, it just means that the components are, there are finitely many components, almost sure. That's what it means to have finite index.
Okay, thank you.
Yeah. So do you know this or like treat like for the free group, like if you have Bernoulli percolation on the free group with infinitely many infinite components, that the co-spectral radius of the cluster relation is less than 1.
Yeah, so I tried to hammer at this problem for a while by just actually kind of trying to figure out, you know, can you get some sort of mixing property or something, or like can you kind of just say what this relation is? And yeah, I don't know. Beyond property T, I don't know. I don't necessarily think that's, I mean, maybe there is a simple proof and I just haven't had enough time, but I don't know from what I attempted so far.
Okay.
Yeah.
Nice. Yeah.
Yeah, so I think that's a good question. I think this is a question we were asked when we talked to, I forget who it was, but Miklos was talking to somebody. I think maybe it was Gabor Peta, I forget. And asked us this question, and yeah, somebody asked us this question, I forget who. And
so I have some vague recollection of somebody, maybe it was Steve Laley, I don't remember, proving that, well, they were looking at Bernoulli percolation on the hyperbolic plane, like you had some tiling, like by fundamental domains of a lattice, and then I think it was looking at connected components, you know, clusters, and their limit set at infinity, and computing the Hausdorff dimension of the limit set.
right.
And this seems very much related. Like I would kind of expect that the Hausdorff dimension of the limit set and this co-spectral radius should be functions of each other.
That sounds like it should be true. It sounds like the co-spectral radius should be some other version of like a dimension or something. It should be some kind of dimension. It's some kind of entropy, so it should be some kind of dimension. Yeah.
Other questions? You know, another thing, this reminds me of Patterson-Sullivan theory. Like if, you know, if you have, if your equivalence relation had a hyperbolic graphing, you were doing simple random walk, this feels like it must be related to some version of Patterson-Sullivan theory. Have you thought about that direction?
We have a bit. I think we didn't maybe think about it hard enough or deep enough. A lot of people have sort of pointed this out to us, and which means that there's probably something there. I myself haven't thought about it much, but it seems like a promising direction. Yeah.
Okay, well, you know, let's thank Ben again. Thanks for a very interesting talk.
Great.
Right. Yeah, well, I guess that concludes our, you know, our mini series on measured equivalence relations. And we have a new mini series that's starting at 2 o'clock today on statistical physics on non-immutable graphs. And so see you there if you're coming. I don't know. And yeah, so thanks, Ben. And I guess that's it until later on today.
All right, great.
Yeah, thanks, Ben. I think I will see you in 10, 12 days in Waco.
I'm still deciding what I will talk about, but I will send you hopefully something by next week. Yeah.
Okay, yeah. Great. Yeah, by next week will be great.
Yeah, awesome. See you
See
then.
you. Very nice talk, by the way.
Thank
Okay.
you. I worded it, I kind of hammered people there at the end, but
No problem. I don't know, you know. I
Right.
pulled up your paper so that I could check things while you were talking, you know.
yeah, so
Just
this thing you asked about this is